As we did last week, we're going to break up the explanation section of this week's module into a couple of different videos, one on friction and the other on inclined planes, which is a common context in physics that we talk about. So hopefully you're finding the various resources useful and interesting and having a good time with your physics learning, putting in plenty of practice and getting plenty of help and support. Encourage you to drop into the discussion board or drop me email or phone, or there's a variety of ways that I can be of help and support. But also remember that your colleagues, your fellow participants in this program are going to be really helpful to you as well. So draw on them in the discussion board and other discussions. Come to the Collaborate sessions. Get involved because it's the best way to learn. Friction isn't a force. We often kind of think about friction as being a force that acts, but there is a force of friction or a force due to friction or a frictional force, but that's a force. We need to describe that force. The same way we tend to talk about weight in everyday life, but in physics we really should talk about the weight force acting on something. It just reminds us that a weight is a force measured in newtons. It's not a mass measured in kilograms, for example. So being clear, precise, careful with our terminology is fairly important. Friction basically relates to the fact that you have two different surfaces in contact with one another and how hard is it for them to slide past each other. So it basically boils down to the interaction of two surfaces with one another. And so it will depend on how rough they are, whether there's some kind of lubricant or other thing between them, whether they are the kind of material that they're made of, and a whole variety of other factors. So we have two kinds of friction: static friction. So if I'm trying to slide my hand on the back of my other hand and I'm pushing and it's not moving, that's static friction. The friction that we're experiencing when things are not moving relative to each other. So in your car, for example, you want the tires to spend basically all of their time in static friction with the road. You want them rolling on the road, but you don't want them sliding on the road. Unless you're doing a burnout, then you want them sliding on the road. But generally, for safety purposes, you want your car tires to be in static friction with the road. I lived in Canada for about 5 years, and the first time I drove in snow was really interesting because in Edmonton, where we were, snow is so commonplace that they literally leave it 30 centimeters deep in some streets and don't plow them, and you just drive on it. It's just normal, no chains, no nothing, just go for it. And that was a shock because I was used to the kind of friction that rubber tires have on tar roads, not to the kind of friction that tires have on snow. So static friction, and then if something is sliding relative to another thing, if you are skiing, you want dynamic friction. If you had no friction, you wouldn't be able to turn because we kind of think sometimes that, oh, the world would be much simpler if there was no friction. But if you've tried running on an ice rink, for example, where your friction is very low, it's really difficult. And we wouldn't be able to run if the rest of the world had no friction. So it's actually a really helpful thing. We want to have some friction. Obviously, in some applications, we want to get rid of as much as we can. So bearings inside a skateboard wheel, we want to use graphite lubricant. We want to get any grit and grime out and so on. We want as little friction as possible. But in a lot of other places, we want as much friction as possible. That's why racing vehicle tires are big and soft and slick. Slick sounds like it wouldn't work, but you've actually increased the surface area. If you've got tread is good for when there's water on the road. When there's no water on the road, you've got a dry racetrack. You want as much surface area as you can get, as big a contact patch. So you'll see motorbikes with quite big, fat back tires, and you'll see ones with tiny, skinny back tires. The more power, the bigger the contact patch you want, because you want that static friction, that ability to grip. So the frictional coefficient is the mu, the thing that we describe as telling us how much friction there will be in a particular situation. And the frictional coefficient is a quality of the two surfaces that are in contact and their relationship to each other. So I've rearranged the same formula in two different ways. Have a look at the bottom one first. The frictional force is mu, this frictional coefficient, times the applied force. So if you're applying a certain force to something, then the applied force is relevant, and how large the frictional coefficient is relevant. But if you have a look at the top, it's the ratio of the frictional force divided by the applied force. Now, both of those forces are in newtons, so the units cancel out. The newton cancels out with the other newton, and so the frictional coefficient mu doesn't have units. So don't write a unit beside it. It's just a raw number, and that's just the nature of the beast. So here's an example, just a quick one, and again we'll give you some other calculations and some examples. If a car weighs 1,840 kilograms, a little under 2 tons, and the coefficient of friction between its tires and the road is 0.82, what's the maximum braking force it can have? Well, the applied force is just going to be the weight force of the car. The weight force of something is its mass times the acceleration due to gravity. So 1840 times 9.8, 18,032 newtons. So that's the applied force. And then we use our equation, frictional force equals mu times the applied force. So 0.82 times 18,032, 14,786 newton. That's as much braking force as there is. So if you exceed that, you'll start to slide. That's as much braking force as those tires on that road can actually yield, given that weight of car. Coefficient of friction, the values of it, typically between 0 and 1. Most often for most normal materials, the values are going to be between 0 and 1. In other words, the frictional force is going to be less than the applied force. In our example a second ago, 0.82. So the frictional force was less than the applied force, and that's typically what happens. There are some very specialized surfaces that are designed to stick and not slide past each other, where you can get a frictional coefficient up to maybe 2, maybe a little higher, but not much higher than that. I see lots of questions that physics teachers assign, and they've clearly just made up the question out of their head rather than found it, and they've used a frictional coefficient of 15. Well, that's ridiculous. That's not realistic for the real world. If we took that back to our car question, the frictional force would be 15 times the weight of the car, which is just nuts. It doesn't make any sense. So it's really important when setting and designing questions to make sure that the answer makes sense, because what you want is that the students are able to get their answer and say, does this make sense? Is this a rational, reasonable answer given what I know about the real world? Right? That's the physics intuition that you want to develop. And if you give them this ridiculous, nonsensical value for mu, you break their physics intuition because they get an answer and it doesn't make sense. It's not rational. So I think that's hopefully a useful point that, and this is just one of the locations in which it comes up. But if you're creating questions, make them realistic in some sense, so that they fall within the bounds of possibility.